Hello everyone, my name is Devendra Kapadia and I'm working here at Wolfram Research as a kernel developer for calculus and statistics functions, and my topic for today is queuing networks, which is really a part of the random process project which Roger's speaking about just right now next door, so kind of we are competing for audience over here. But so basically a queue is something really simple to describe. So let's say you go to a bank on a certain day and you go into the queue, and then at some point one of the tellers will serve you and you're out. So queue is something really simple to describe, and one has lots of queues in life. Life is just queue after queue after queue. So for example, some of you may have taken a flight to arrive over here, so you go to the airport, you check in your luggage, that's one queue, then you try to board the aircraft, it's another queue, get off the aircraft, another queue, come out. So by the time you've come, you've probably gone through 8 or 10 queues, and we kind of take queues as a part of life. Another example, some time ago my internet connection failed, so I called up tech support somewhere in India, I think, and they replied, they put me into a queue, and then someone put me on another queue, and then eventually everything got sorted out. But that's life. I mean, you queue after queue. And talking about myself, I work as a kernel developer, so the most important queue in my life is the bugs queue. I know that may not be something very exciting for you, but it's critical for me. I get bug reports coming in a few times a week. I have about 50 functions in Mathematica. Some of them are kind of popular. So just to give you an example, this year my bugs queue has looked like this. I had 130 reports coming in as of yesterday, and I fixed 139, so I had a bit of backlog from last year, cleared that. So I'm doing quite well this year. I'm quite pleased that things are under control. But in any case, that's the way queues are. They are there. We kind of learn to live with them, and we have a sense of what we're willing to tolerate before we blow up and say, that's enough. So that's queuing in real life. And if you're running a big business or some big enterprise, then what you want to do is to put a few numbers to your queue which tell you whether things are really under control or not, and that is done by what's called queuing theory. So what I'll do now is to speak a little bit about queuing theory, which is a branch of mathematics to which all this belongs. So question is, what is queuing theory? Well, that's a very simple answer. Queuing theory is the mathematical and statistical study of waiting lines. That's what queuing theory is. Oh sure, I can do that. Yes, I think I'm now past the first page, so I should be okay now to magnify. I'll try and go up, but okay, this is where it was actually. A little better? One more? Okay. Yeah, let's see if that works. Okay, good. Okay, so what is queuing theory? Queuing theory is the mathematical and statistical study of waiting lines. So that's what mathematics is good for mathematics and statistics. So what we did in version 8 was to build up all the stuff which you now need to do queuing theory in version 9. The question is, what does queuing theory aim to do? Well, queuing theory aims to study two things. One is the so-called transient state of a queue, namely when things are just settling down and not quite stable. And then eventually the queue goes into steady state. In other words, things are still not completely deterministic. You're still doing statistics, but now you have some sense of what's going to go right and what's going wrong, and so you can actually use mathematics at that point to study it. So you have simulation for the transient state and analytical methods for the steady state. So question is, where do you find applications? I didn't know that until I began studying this subject. And the biggest fields are computer systems performance. There's a huge field over there. The internet and other networks, customer service, and public health is a big area, because let's say you're running the emergency room, you want to make sure your queues are in control. You can't afford to let people just come in and not have someone to serve them. So queuing theory really is a huge thing for today's enterprises. So now let's talk about some of the people who have done queuing theory, and I know you might be from one country or other, but I should say that literally every country has produced some good queuing theorists. I'll just mention three over here. There's A.K. Erlang from Denmark, who actually I would say is the father of queuing theory, and he worked for the Copenhagen telephone company and did his best to work over there. So Erlang is the father of queuing theory. Then there's John Little, who's actually at MIT. He's an institute professor, and his great contribution was he proved a law called Little's law, which is really simple. It's called it says L equals lambda times W. So if someone says, do you know queuing theory? You say, yes, I know L equals lambda W, and you're done. You know. So they say, okay, this person knows queuing theory. So what's L? L is the queue size, W is the queue waiting time, and lambda is the arrival rate. So that's John Little. And then for me, the favorite figure in all this is Kleinrock, who actually is at UCLA. He has produced 47 PhDs under him. I think a student of Claude Shannon, and he's the person who applied queuing theory to develop the ARPANET a long time ago. So Kleinrock is, to me, the modern father figure for queuing theory. Okay, so finally, how do you describe a queue? You know, Laplace said that probability is common sense reduced to calculation, and that's true of queuing theory as well. Queuing theory is just common sense reduced to calculation. So question is, how do you describe a queue? Well, a queue can be described by the arrival pattern. How do people arrive? How do they get served? How many service channels are there? How many servers do you have? That's important. Does the system have finite capacity or infinite capacity? To give an example, you might only have 3 phone lines, and the 4th person who calls is told, sorry, there's no room for you. That shouldn't happen, but that's system capacity. And finally, what's the initial state? So let's say you come in the morning into your office and there's a huge queue of email waiting for you. So your initial state is quite bad, and you wonder whether you ever get through that, you know. So Kendall actually gave a very nice notation for all this. He said, if you want to describe a queue, all you need to do is to say, give the arrival, service, number of service channels, system capacity, and initial state. That's all. So that's called the ASCKI notation for a queue. So that's my brief introduction to queuing theory, and now we go into Mathematica 9 and into the analysis of single queues. So what we've got now is a very nice, I would say, mini super function called queuing process, which kind of can be used to analyze any queue in the world basically. So it's a very simple function. You say queuing process, then you say, okay, I need to go back to Kendall. So what did Kendall say? He said, give the arrival, give the service, which of course distributions, number of channels, system capacity, initial state, and you're done. Well, that's not too good because you still need to give 5 things. So we say, okay, if you don't give C, then C must be 1. If you don't give K, K must be infinity. And if you don't give I, then I must be 0. So to specify a queue, you only need just 2 arguments over here, the first and the second argument. But you can go a step further and say, well, many queues are Markovian, which means that the arrival is exponential and so is the service. And in that case, what you can do is to simply say, give the arrival rate and the service rate, and you're done. So Mathematica 9 really makes it trivial to set up a queue and then analyze it. This took a lot of work to get to, but essentially now you can reduce queuing theory to a single function in Mathematica 9. Okay, so how do you simulate a queue? So here's a queuing process, like I said, arrival rate lambda, service rate mu, that's all. To simulate it, let's use a function called random function. Okay, that's the random function for Mathematica 9. Let's look at the queue. So you have 2 columns over there. The left-hand column is the event times, arrival or departure, and the right-hand side is the number of people in the system. So initially there was no one, then one person came, a second one came, a third person came, a fourth person came, and then people woke up and started serving them. So the queue went down, 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 and so it goes up and down, but that's the way queues are. So question, how do you picture the queue? Well, you simply use list line plot, and when you do that, in this case, you see the queue is not completely stationary, not static, but things are under control. It's kind of got a steady state because the arrival rate 3 is less than the service rate 10. Okay, what happens if the arrival rate is larger than the service rate? Well, in that case, what you see is the queue just blows up and shoots off to infinity very soon. Okay, so question is, what happens if you have only a finite system capacity of 15, let's say, So only 15 people out in the queue. Well, in that case, things don't look so good, because every time the 16th person comes, he's kind of thrown out of the system, so the system is bounded above by 15, as you can see over here. And finally, what happens if you have an initial size of 50? Well, if that happens, then initially you'll have lots of customers in the queue, but then as time goes by, it dwindles and the number goes down to something which is nice and stable. So that's about simulation, and now on to the steady state. Well, I thought a lot about this, and I said, okay, if you have a queue in steady state, one should have just one function that gives you a picture of what's happening for a steady state. And this function, Mathematica 9, is called queue properties. So you say queue properties of the queue, that's an MG1 queue. That means Markovian arrivals and Erlangen departures in this case. So if you say queue properties, lo and behold, you get back a nice table with all the properties specified to you. And this is what people want, really. They just want to have a summary table which at a quick glance will tell them what's happening with the queue. So for example, you want to know the mean system size, it's just there. So it combines Mathematica graphics, grid, etc. with symbolic computation, with all kinds of other things. Okay, so now the genuine application of all this, here is a brief introduction to an area of mathematics called call center mathematics. In the last 5-10 years, call centers have grown up all over the world, in India particularly. So you make a call to AT&T for internet, it goes to India, goes to someone who's over there doing tech support, and these places are huge. Okay, they're not like our tech support, very nice specialized groups. They have hundreds of people in them. The question is, how do they make money? Well, they make money by employing just the right number of people. If they employ too few people, then no one's going to come to them because there are service problems. If they employ too many, they lose money. How do they do it? Well, they use queuing theory. So in fact, there are entire schools of call center mathematics these days. And in Mathematica now do this because we have these two things called Erlang B and Erlang C. What's Erlang B? Erlang B is the probability that if there are only a finite number of servers and a finite capacity, then you will be kind of asked to leave the system. That's a loss probability. If that happens, the customer is lost and there's a loss of revenue. That's not good. The other one is more common. You make a call to some tech support and they say, okay, your call is very important to us, please hold, okay? And that's called Erlang C. So Erlang C is the mathematical version of your call is very important to us, okay? So, and we have two functions to do that. We got Erlang B in Mathematica and Erlang C, which will do just those two formulae for you. Now, I worked on this function called probability for version 8, and you can use it to give a really nice, elegant verification of the formula for Erlang B. So what's Erlang B? Erlang B is a probability that you have a system with capacity C, and there are exactly n customers in it. You are in the stationary state, and make some assumptions, and you get this not so bad but not so nice looking answer. And what Erlang B does is it just makes that answer a lot more elegant thanks to our special functions people, and you check the two are the same and you're done. So in Mathematica, Erlang B is just an incomplete gamma function computation. And if you look at the web, people spend a lot of time just trying to figure out this gamma function computation, but now we can do it trivially. Okay, so that's one extreme, okay? If you like mathematics like I do, then that's good. But you might say, oh no, I'm a Wolfram Alpha fan, which a lot of people are these days, then what do? Well, in that case you can build a calculator. Here's a calculator which I didn't build myself, I'm not that good at these things. Henry Kwong helped me to build. So that's the kind of calculator that retails for $95 on the web. People pay for it because they want to calculate how many people do I employ for this particular call center. So for example, if you know your traffic is 30 calls per hour and you would like your customers to have a delay probability of at most 0.1, then how many people do you need to employ? Well, you need to employ 39 people. But you might say, oh, customer is king, so let me push that up to 0.01, push it down, what do you call it? So 0.01, and you calculate, and now you better employ 45 people you want that to happen. But then you might say, oh, the customer can wait, who cares? And then you only need to employ 32 people. But you can't go too high, because if you go towards 1, you are in trouble, because then your people are going to be leaving you. So that's the kind of balance that when people strike in these call centers. They make money by just figuring out how many people do you need to employ. And now in Mathematica, you can just do it in a minute.
So the assumption is that the salaries are the biggest expense?
That's actually true, yeah. Because everything else is just hardware, and so that's what I'm told. I'm not an expert on this, but I did a lot of research on this, and I found that there are calculators. There's a whole school called School of Call Center Technologies, and they just do teach this kind of stuff to them. Okay, and they just need a gamma function. Now we've given it to them. So that's our contribution to the world. Okay, so that's about call center mathematics. And now I move on to queuing networks, a slightly more complicated area. So what's a network? Well, a network is just a collection of queues with kind of routing probabilities between those. So you go to a restaurant and you first enter the queue to pick up your food, then you enter another queue to pay for the food, etc. You go to an airport, oh gosh, let's not talk about it, there's just lots of queues over there. But these queues occur everywhere. They occur in your email system, they occur on the internet, etc. And we have a nice function in Mathematica 9 called the queuing network process function, which can be used to analyze queues. Okay, so what is queuing network process? It requires an arrival rate for each channel in the queue network, service rate, a routing probability matrix, and number of service channels, and system capacity. So very simple function to set up, and the queue could either be, the network could either be open, like at an airport, or closed. And a good example of a closed network is our own MathLM, the license manager. So you buy 100 licenses from Mathematica, let's say university, and then the license go out from the main server to people, then they come back. So at no point do you have 101 licenses, nor do you have 99. They just circulate in the whole network, and your question is, how are the network licenses being used? Okay, so who did work on this? Well, there's Jackson, who did really good work. There's Gordon Newell, who worked on closed networks. And there's Buzen, who actually taught Bill Gates about operating system at Harvard. So I guess he's quite an important person. Okay, so as an example of this, here's a nice one. You have a central server. It sends out messages to 2 other servers with some probability. And it's a simple network. Question is, where is the bottleneck over here? It looks a bit messy to set up, so let me not worry about it. Let me just go ahead and set the network up. And I'm going to now simulate it for a little bit. Let's simulate it. And then I go here and just do a plot. So that's node 1. That's node 2, that's node 3. Question is, where's the bottleneck? You just stare there, and it's clear the bottleneck is at the first node, because you have lots of people jammed up over there. So either you put in more servers over here, or you do something else, but that's where the bottleneck is. Okay, so if you like tables rather than graphs, you want to show your boss, then there you are. You can do a table. And that's node 1, that's node 2, that's node 3. Where's the bottleneck? It's at node 1. So what you have now is a very convenient way of picturing these queues. Let me just, so that's queuing networks, and again I think Mathematica 9 is really quite good at all this. It's a big area, but we've made some really good progress over here. Okay, so I have just a bit more time left, and I should now speak about documentation and project ideas. So we have 5 functions area. There's queuing process, queuing network process, queue properties for the summary, Erlang B and Erlang C, just 5 functions. But I did put in a lot of effort into documenting them. So if you go to the guide page for queuing processes, if you have a copy of the beta, then it's a really nice page. It looks different because it's more finished now. Okay, we are doing better day by day for Mathematica 9. But so here's the page with the flag under development, which says that we're not quite done. but you can see all the functions over here. You can click over here, and I've tried to give something for the average, let's say, professor, trying to look through over here, see whether it's got everything for him. And here's a scope, for example, and you can see all kinds of queues, every kind of queue that you would see in the standard textbooks. Okay, so now, what can you do with this? Well, one thing you could do is to write demonstrations for this area. In fact, there's some really good demonstrations from early on. There's one by Heike Ruskipa, which I quite like, on MM1 queues. Another one by, I think, Karl Heine and Stan Wagon on multi-server queues. So here's one of them. I just picked it up from the web, and you can see over here that it's a demonstration on simulating the MM1 queue. And if you scroll down a little bit, then right over there is Little's law, L and W, etc. But in Mathematica 9, this is all really quite trivial. So if you happen to be teaching at high school or college level, you could certainly try and ask the students to do a demonstration in this area, or you might actually make them do a project on queuing theory by actually going to a local restaurant and seeing how queues work over there. But I think this is a really good piece of applied mathematics compared to a lot of things I've seen over here. There are lots of applications in math textbooks, but this one is real. I mean, it's really applicable. It can be used to make money, really. One of the few times you can see mathematics really used to make money, but it's really quite useful over here. Okay, so I guess I'm almost done. And my main point is that Mathematica 9 has several functions for studying the transient state of queues with simulation, or the steady state queue behavior with queue properties. But what are you doing? Mathematica 9 is really quite well equipped over here. What's going to happen next? Well, I don't know. We haven't finished Mathematica 9, but we will in a couple of weeks. And then beyond that, we'll either go into queuing networks, that's a big area, or we might just go into a more general area called discrete event simulation. The point being that these events happen randomly, you need to simulate them, and that's quite a hard problem. So that's what I've been doing for the last couple of years, apart from other things, and some DSOL, etc. But I thank you very much for all having come over here. It's nice to see people so interested in this subject. It's a beautiful subject. If you have questions, I'd be happy to answer them, but let's stop over here. Thank you.